So things that we're going to discuss today are how we write chemical reactions, how we balance chemical reactions, and on the related note, what is a concept of a mole, okay, which is one of the central concepts. So a mole, and this is one of the few instances when this introductory slide is actually useful. A mole is a counting quantity. You see these terms like dozen? How many is a dozen? 12. When we use the word decade, what do we refer to? 10 years, but still it's counting. You see what I'm saying? So a mole is a number, it's a count. It's called Avogadro number. So Avogadro number shown here, it's huge. It is what, 6? So it is like trillion times, more than trillion times more than people on Earth. Like it's enormous. One of my favorite examples of how large the Avogadro number is, so Earth is about 4.5 billion years old. If at the moment when Earth actually formed, somehow we would have 1 mole, that number, of dollars. And we would spend $1 million every second since then, which is a lot of spending even by American standards. We would not burn through a half of it for 4.5 billion years. It's an enormous number.
How did anybody ever arrive at that number? Like, how could anybody ever know that's like, that, you know what I'm saying? Like,
yes. I was hoping that nobody would ever ask me that question because I don't know the answer to that. Originally, Avogadro, so the Avogadro's law pertains to the gases. It's a bit of a tangential idea. So Amedeo Avogadro figured out that 1 mole, so 6.02 multiplied by 10 to the power of 23 atoms of a gas, or molecules of a gas, at the room temperature and atmospheric pressure, will always occupy the same volume. So basically, he figured out that a certain amount of gas will always have the same volume regardless of what this gas is. I think that what brought him to the idea that, we should operate, when we talk about atoms, not with grams or milliliters or pounds, but with numbers of particles. Okay? I'm sorry about that. Okay, all good? So, I am absolutely serious. I'm going to be asking you, do you understand what I'm talking about? I want 100% understanding among all of you, okay? Like, I'm dead serious. So, a mole is the same categorically as a dozen. You can say a dozen of eggs, and it will mean how many eggs? 12. Or I can say a mole of eggs, and that would mean 6.02 multiplied by 10 to the power of 23 eggs. Does that make sense? So when we say that we have 1 mole of an element, it means that we have this number, 6.02, 10 to the power of 23, atoms of that element. So no matter what element that is, it's going to be the same number of atoms. Okay? Is that clear? We can use that term for anything. I mean, we can use that term for eggs. It's just a shitload of eggs. it's unimaginable amount of eggs. Like nobody will ever have that many eggs ever in the history of humanity. But when we start talking about really tiny particles, like atoms, it's a lot of atoms, but they're really tiny. So when they're put together, it's conceivable quantity. We can look at it, okay? So when we say that there's 1 mole of sulfur, it means that we're dealing with this number of sulfur atoms. When we say that there's 1 mole of sodium chloride, though, we use the term formula units. So I'm going to check your understanding. So when we talk that we have this number, 1 mole of molecules of water, we can say that, right? Because water is a molecular compound. Do you follow? So each water molecule is 2 hydrogens and an oxygen. Agreed? So it's a unit. It's a discrete unit. But on the other hand, if you think about sodium chloride, it's an ionic compound, which means there's no molecule. When you look at water in a bottle, it consists of discrete molecules. When you look at sodium chloride crystal, it is sodium chloride. Sodium chloride. Does that make sense? It is not composed of discrete NaCl units. This is why, when we talk about ionic compounds, we don't use the term molecule, we use the term formula unit. I'm going to give you one other example. Magnesium chloride. It's an ionic compound. For every magnesium atom, well, ion, there are 2 chloride ions. Does that make sense? But there's going to be another magnesium and other 2 chlorides, and so on and so forth. So we can't say that this is the unit and not this. So we don't have discrete units, so the statement magnesium chloride shows us simply the ratio between the positive and the negative ions in that crystal structure. Before we move any further, does that make sense? I don't know how to read your minds. So if you don't tell me, no, it makes no sense, I'm going to move on. Deal? Okay. Essentially, there's a conversion factor, which tells you that 1 mole is equivalent to that number of particles, or that number of particles constitutes 1 mole. Questions on this? So I can absolutely go back up. Okay? And we are going to use these conversion factors to go from the amount, the moles, to mass, grams. Let me know when I can move on. I don't want to push you. Good? Okay. So we've already seen some, formulas, and we've seen subscripts. So let's look at what these subscripts mean. So we mentioned that before, that a subscript, like a molecule of aspirin, right, means that each molecule of aspirin contains 9 carbons, 8 hydrogens, 4 oxygens. Okay, I can make it larger. Does it help? Okay. So in order to demonstrate it to you, you see that big ass molecule in the center? This is a molecule of aspirin. Every black circle is carbon. Every white circle is hydrogen. And every red circle is oxygen. I want you to help me count black circles. 4, 5, 6, 7, 8, 9. Okay? All good? Now we're gonna, I don't know, let's pick blue for the white circle. So how many hydrogens? 3, 4, 5, 6, 7, 8. Are all hydrogens accounted for? And now oxygens, 1, 2, 3, and 4. Right? So we basically come back to the formula that we've been given. The subscripts tell us that one molecule, one unit, contains 9 carbon, 8 hydrogen, and 4 oxygen atoms. Does this idea make sense? Okay. So, do you agree with that statement on the bottom? Yeah? So now, I'm going to make this quick transition, and I will tell you that if we take not one molecule, but 1 mole of aspirin molecules, within that 1 mole of aspirin molecules, we're going to have 9 moles of carbon atoms, 8 moles of hydrogens, and 4 moles of oxygens. And at this point, I want you to question yourself whether you really, whether it makes sense, whether you understand it or not. Because I can give you an analogy. How many, let's say an average football team in NFL has 3 quarterbacks, okay? The entire roster. And say 6 running backs. I'm not considering the rest of it, okay? So one team, 3 quarterbacks, 6 running backs. In one division, there are 4 teams. How many quarterbacks total are in the division? Huh? 12. How did you get to this? Say again?
4 times 3.
Thank you very much. Yes, 4 times 3. So how many atoms of carbon in one molecule? 9. What is a mole? And it is a number. It is a number like 4 or 76. Does that make sense? And just like AJ calculated the total number of quarterbacks per division by multiplying the number of quarterbacks in a team by the number of teams, what we do, we take number of carbons in a molecule and multiply it by the number of molecules, which is a mole. Okay? Fair? Good? So that allows us, if somebody asks us, how many moles of a particular atom can we find in 1 mole of a compound? We need to take the number of atoms in a molecule and multiply it by a mole. Okay? Now, before we get any further, forget about aspirin. How about some practice? So the formula of glucose is C6H12O6. Okay? So 1 mole of glucose contains how many moles of carbons?
6.
Excellent. Here's my other question. If I will have 5 moles of, if you don't mind, I'm going to call glucose capital G, how many moles of carbon?
30.
Okay. I'm a bit disappointed that I didn't have to use the conversion factors with you, but on the other hand, good job. Okay? If you start struggling, remember that you always can do this. You can do a conversion factor. 1 mole of glucose contains 6 moles of carbon, right? That's a 30. Right? All good? Don't worry. I understand. So I want to slightly, we're going to talk about molar mass. I want to slightly correct the definition. How many atoms are in 1 mole of carbon? How many atoms? It is not a tricky question. How many atoms are in 1 mole of carbon?
6.
That number. Use just that number, right? That number. 6 whatever, right? How many atoms are in 1 mole of neon? Well, you can look back at the periodic table. The atom of carbon and an atom of neon, are they different? Do they have different atomic masses? Yeah. Carbon has 12, give or take, right? You see the bottom number? Right? Neon has 20. Which is heavier? Neon. So if you take 1 mole of carbons and 1 mole of neons, which mole will have a greater mass? Neons, because the atoms are heavier. Does that make sense? Now, did I hear dissent or it was confirmation? Make sense? Okay, good. So, basically, the molar mass constitutes the same number that you see under the chemical symbol in the periodic table. So if you start looking at carbon in that fancy periodic table that we have on the wall, it's not just 12.01, it's 12.0108 grams. Okay? And this is a mass of 1 mole. This is basically a definition of molar mass. Let me do some other exercise. Look at the periodic table and tell me what is the molar mass of aluminum. Molar mass. How much? Point. Units? If it's a molar mass? Grams. So 1 mole of aluminum has a mass of 26.9815. Does that make sense? Take a look at what I wrote on that page. Is this a conversion factor? Yeah, it is a conversion factor. It tells you that 12 point whatever numbers gram of aluminum constitute 1 mole.
So would that be the answer? Like if you ask how, would that be it? Like would it have to be written out like that?
I'm not sure what you're asking.
If you're asking what is the molar mass of the atomic number, would it be that, like would it have to be written like that, or would the answer be 12.0108 grams?
Oh, okay.
Sorry.
So, molar mass is the mass of 1 mole.
Yeah.
So now, let me ask you a textual question. What is a mass of 1 mole of lithium? 6.941 gram. Period. If I ask you what is the molar mass of lithium, usually we do it capital M and element. It's going to be 6.941 grams per mole. This is basically an equivalent of writing 6.941 grams over 1 mole. Did I answer your question?
Yes.
Excellent. Or we can say, that 1 mole of carbon here constitutes, we can flip it. It constitutes 12.01 grams.
So for the atomic mass, like if we're not figuring out how many moles are in a particular element, like for carbon, with the 12.01 we see on the periodic table, would that be expressed in like atomic mass units? You know what I mean?
No, sorry. When you look at the periodic table and you see 12.01, this is the atomic mass or mass number. And if I ask you, what does that mean? It means that 1 atom of carbon weighs 12.01 atomic mass units.
Yeah, like that's what I was...
Yes, but if my question is, what is a molar mass of carbon? Your reference point, like this is going to be an atomic mass of carbon, a molar mass of carbon, in grams per mole. Number is the same, units are different. Did I answer your question?
Yeah.
Okay. I guess, we explained this concept extensively, right? So if I ask you, let's see, can you tell me what is the atomic mass, or molar mass of gold, 79th, or
197 grams.
So again?
Gold, 197.
Yeah, 197. I'm looking at like more, but yeah, 197 grams, right? We round it up. Does that make sense? Gold is 79, okay? So Zach just rounded up to the whole number. It's okay.
It's okay to round?
Okay. If you need to find the molar mass, you look at the mass number in the periodic table. Now this is just very illustrative, showing you 1 mole of different elements, different substances, okay? It greatly depends on how dense they are, for the most part, and density greatly depends, if we talk about molecular compounds, on the size of a molecule. So you see, this is table sugar. It's a lot. This is one of my favorite compounds. It's potassium bichromate. If it is mixed with concentrated sulfuric acid, it, over the time span of maybe 2-3 days, can probably dissolve a human being completely. It's very effective in washing dishes. It is used for washing dishes. Extremely chemically active.
Dishes won't disappear?
No.
You don't have the acid.
That was our organic chemistry lecture, third year of college. So now it's pretty straightforward how you calculate the molar mass of an element. Am I right? Now, what if you need to calculate a molar mass of ethanol? So how many carbons do we have? What is the molar mass of carbon? 12. Yeah. How many hydrogens? What is the molar mass? And how many oxygens? What is the molar mass? 46 grams per mole. AJ, question?
Yeah, I was just seeing if the numbers were rounded or anything.
We will always round, just for simplicity. Okay? So first of all, you got to figure out how to convert between the mass of something and moles of something. So molar mass is essentially a conversion factor. We already talked about it. And you can write it both ways. It all depends on what you want, what result you want. Okay? So here's the question. You have 737 grams of sodium chloride. You have to go, hear me out, from grams to moles. So in the conversion factor, what should be at the bottom? Grams. So 1 mole. What is the molar mass of sodium chloride? What is the molar mass of sodium? 23. What is the molar mass of chlorine? 35. $58. Does that make sense? I mean, I don't care about the answer. The concept, how we did that. Does that make sense to you all?
Oh, yeah.
All right. Now tell me, how should I arrange my conversion factor? How many moles? How many grams? Oh, this is not complicated. Huh?
18.
Say again?
16 for the oxygen.
16 for the oxygen and 2 for hydrogens because each hydrogen is 1. Does that make sense? If I'm going too fast or skipping steps, tell me.
This is our action spread.
Okay? Make sense? And then the answer is whatever. Questions on these conversions? Totally expected in the exam.
I mean, all you're really doing is just adding the mass number, pretty much.
Yep.
After rounding it up.
Yeah. Glucose. What is the molar mass? No, just tell me what I need to do.
Add them all up.
6 multiplied by 12 multiplied by 6 multiplied by
16.
whatever. I mean, seriously, you can press buttons. Make sense? And then it's going to be, obviously, grams per mole. Okay? So this is the map of conversion factors, how you go from, here and there. Okay? So if you want to go from grams to moles and back, you use molar mass. If you want to go from moles to numbers, you use Avogadro's number. Do you follow? So, I'm going to do a practice problem with you. I'm going to keep using glucose. So let's say we have 100 grams of glucose. Okay? I ask 2 questions. First, how many glucose molecules? Stop. No. How many glucose molecules in 100 grams? Question number 2. Mass of carbon in 100 grams of glucose. So let's address the first question. You have to go from 100 grams to number of molecules. Do you agree with me? So you start with 100 grams converting to moles. Making sense? So glucose, 61696 plus 12, 108 plus 72, 180. 180 gram per mole is the glucose molar mass. What should I put as the first conversion factor? Grams where? And what should I put as the second conversion factor? Now, yes, where should mole go? What should go on top? Does that make sense to you?
So you're canceling out mole.
Yep.
In the second step, that's why you put it at the bottom.
Yep. Yep. Oh. This. I told you when I was in high school, I'm not kidding. The calculators in a physics class were banned. We had to do all calculations in the head for the entire high school. On the bright side, she said, like, round the numbers. It's fine. Okay? Does that make sense? Question so far? I need to answer second question. what is the mass of carbon, just carbon atoms, in 100 grams of glucose? Okay? So,
You probably have to isolate the mass of the carbon in that equation.
my suggestion, when you have any chemical calculations, they all should include a step with a mole. Either they start, they have it in the middle, they have it at the end, but mole is ultimately involved. So, 1 molecule of glucose contains how many carbons? 1 mole of glucose contains how many carbons? Moles. 6 moles, right? 6 moles of carbons. Good? Can we find how many moles of carbons, carbon atoms, are in 100 grams of glucose? Yes. So, we have this 100 grams. Can we find the number of moles of glucose? Yes? We already did that. Okay? So this is moles of glucose. Okay, mole, I'm going to put it here, of glucose. So now we have to get from moles of glucose to moles of carbons. What do we put in the bottom? Of glucose. Look, we have to go from moles of glucose. 1 mole of glucose contains how many moles of carbons? Yes, 6 moles of carbons. Now we have to get from moles of carbons to grams of carbons. So which conversion factor do we have to use? Molar mass of carbon. So what goes on the bottom? 1 mole of carbon has a mass of carbon. Perfect. I frankly have very little idea. It's like 40 or something. I think it's 40, yeah. Does that make sense? Okay. This is the first time I do this example. This 40, very nice round answer, was absolutely unintentional. I had no idea. Okay. Does that make sense? You can see that I was very reluctant to use conversion factors when we moved to States because in Russian school, like chemistry, we taught differently. But now it becomes almost a mechanical exercise. Here's the deal. You may have noticed I put units all the time in these calculations. Please put the units. If you use the wrong conversion factor, your units will stop making sense. You're like, oh, I need to flip it. I need to use something else. I'm going the wrong direction. Does that make sense? Please do that. Questions on this transitions? No? Okay. So now we're going to learn how to write balanced chemical equations. So first of all, a chemical equation is when atoms in substances are rearranged. Basically, what I'm telling you is, when you have 2 hydrogens and 1 oxygen, and they burn. Like, they actually, if you mix them in a proper ratios, it will explode. You're going to get water molecules. So you see, hydrogens and oxygens, they are rearranged. This is a chemical process. If you have liquid water and you evaporate, and it's water vapors, were atoms rearranged? They were not. It's a physical process. It's not chemical. Good? So what can serve as the evidence? Change in color, evacuation of gas, formation of precipitate, increased change in temperature, increased temperature, sometimes decreased temperature. Good? We're going to learn more about those evidences. But when you write an equation, there are some conventions. You write it from left to right. On the left, there are reactants, things that you mix. On the right, there are products, things that you get after mixing. Okay? Is that clear? When you have an arrow, it constitutes the direction. This little triangle, which is a delta sign, means that you need to heat up your reaction. Okay? I mentioned that reactants are on the left, products are on the right, and they are separated by pluses. Okay, so we can say that in this reaction, carbon plus oxygen, if you heat them up, you will get carbon dioxide. Make sense, everyone? Okay. Now, this can be important. It usually is important, but very often when it's not critical for our understanding, I'm just going to skip those, okay? Like if we have carbon and oxygen, carbon is going to be coal and oxygen is going to be gas, so everybody knows what physical state they're in, right? But if it's unclear, then we can put it. So this is the summary. I believe these and this make sense. No questions about them, right? The last thing I want to mention. These denote physical state. Aqueous means aqueous solution. Let me explain. Crap. Give me a second. Okay. Okay, so I'm trying to come up with a reaction that would be different whether the reactant is solid or aqueous. Here's the thing. Sodium hydrosulfate, okay? You add, let's say, barium chloride, okay? And you're going to get, and both of them are aqueous, okay? So you see this solid on the right? This is a precipitate. So you took two solutions, mixed them. Do you see what I did? And got yourself a reaction, precipitate as formed. Am I making sense? Now, one of the most boring reactions that I ever had to deal with solid sodium hydrosulfate is heated. It took me 3 days. It was in our chem lab, I mean, not 72 hours. It took me about 12 hours to get there. Sodium persulfate. It is solid. It is gas. So you see, it's the same ionic compound, but it behaves differently whether it is solid or it is in the aqueous solution. Did I answer your question? Okay. Atoms in chemistry cannot be created or destroyed. Okay? The law of conservation of mass. So when you write a reaction, the number of atoms on the left, every atom, and the number of every kind of atom on the right should be the same. So in this reaction of formation of water, how many hydrogens do we have on the left?
4.
Atoms. 4. We have 2 diatomic molecules. How many oxygens? How many hydrogens do we have on the right? 4, because each molecule of water has 4 hydrogens, and 2 oxygens because each molecule of water out of 2 is 1 oxygen each. Make sense? You all? Okay. You just need to state, so how many atoms of phosphorus in the example A do we have on the left?
4.
How many, oh, that's going to be, I like it. How many atoms of bromine?
12.
Boring. 12, yes. Because how many molecules of bromine do we have on the left? 6. And how many atoms per molecule? Yes. How many molecules of phosphorus tribromide molecules do we have on the right? 4. How many phosphoruses? Phosphori? I don't know. Atoms of phosphorus on the right. 4. How many atoms of bromine?
12.
Balanced? And here, how many aluminums on the left? Irons? Oxygens? On the right, irons, aluminums, oxygens, 3. Okay. So now we're going to balance the reaction, and I'm going to give you what I use. When you balance reactions a lot, eventually, for simpler ones, you will start just seeing, oh, I have to slap this number here and there, okay? We're going to do the long route. Oh, sorry. Okay, so iron oxide. It's a weird iron oxide. It's like a mix of 2. They just did it for like complexity. Reacts with hydrogen gas. How many atoms are in a molecule of hydrogen? 2. It's a diatomic molecule. And they produce solid iron and water. First question, is it balanced?
No.
No. It is not. So what I usually suggest to do, you put the elements in the column under the arrow. Oxygen and hydrogen go on the bottom. Okay? Always. Does that make sense? Okay? Now you start writing down how many atoms of each element you have in the unbalanced equation. So how many iron atoms do you have right now on the left? Oxygens, hydrogens, on the right, iron, oxygen, hydrogen. So first we need to balance iron. Agreed? What do we need to do?
There needs to be put a 3 in front of the FE.
Okay. So now we have 3, 1, 2. What about oxygen? Can we balance oxygen? Yes, we're going to put 4 in front of H2O. Hold on. 3, 4. How many hydrogens on the right do we have now? So again, how many hydrogens right now do we have on the right? 8. We're good with iron? We're good with oxygen? What do we need to do with hydrogen? 4. Because if you put 2, it's good. Yeah. And now we have 3, 4, and 8. Does that make sense? Done deal. You will have to balance equations on the second exam. Now, it's all multiple choice. So by balancing what you're going to have an unbalanced reaction, and you will have to pick the answer that contains correct coefficients. Okay? So for this one, if I would present it, the answer would be, like correct answer, 1, 4, 3, 4.
That's how we present it.
Okay. Can I kill most of it? Let's convert this question into multiple choice. So multiple choice question, balance the chemical equation, blah, 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 okay? This is the reaction. So your first answer is, that I give you, answer A, is 2, 4, 1, 4. It means that 2 goes here, 4 goes here, 1 goes here, and 4 goes here. Will it balance the reaction? No. Will you pick A then? You won't. B. I'm making up numbers. 3, 1, 4, 4. Is that the right answer? Is that the right answer?
Yeah.
You pick it. Does that make sense now? Yes.
So the coefficients will go in the order of which like, the question's written, because the question has the order of like these are the reactants, these are
The answers always will go, like the coefficients will be
the order.
order of the chemicals in the physical, literal reaction that we will see on the page. Okay, does that make sense? Okay. Polyatomic anions. Remember, when you treat polyatomic anions, you will try to balance individual elements in the polyatomic anions. You're going to go bananas. So instead, you have to treat a polyatomic anion, such as phosphate, as a single entity. Okay? So here's what we're going to do. We're going to go through this learning check. Then we're going to go back to this and try to balance the reaction there. How does that sound? So first of all here, what would be the proper coefficients? So, okay, let's take a look. 2. So 2, 3, 4, 3. Does it check out? How many irons do you have on the left? How many oxygens?
6.
Carbons? How many irons on the right? Oxygens?
6.
Carbons? I think it checks out. You lost?
I'm lost, yeah.
Okay. We're not going to skip the step then. Let me write down the reaction again.
So if, yeah,
Yes.
yeah, so you have 3 of 2 oxygens, so that is 6 oxygens altogether. But since there isn't a little number in front of the C, then it's just 3.
Folks, how about we're going to run through it really quick? We can do really quick. You can help me to do really quick. Irons on the left. Carbons. Oxygens. On the right, iron, carbon, oxygen. So we're going to start balancing with iron, right? What do we need to put in front of iron on the right? Okay, we do follow. Okay. So iron's fine, carbon's fine. Now we need to balance oxygen. This is what I love. Can we, I love about English language, can we put a fractional coefficient in front of CO2? Behold. I can. I'm not allowed to. Like, can you murder a person? You can. You shouldn't. Okay? Does that make sense? So, right now, right at this moment, how many irons do we have on the right? Oxygens. Carbons. 1.5. Can we finish balancing? Sure. Are we allowed to do that? So how do we get from 1.5 to a whole number? Multiply it by 2. Can we multiply only carbon by 2? We shouldn't. We should multiply everything by 2. So, Kaylee, are you with me? So, we multiply everything by 2. That step, does that step make sense? After all this trickery, how many irons do we have on the left? I'm asking Kaylee.
So we have 2 times?
Yes. Oxygens? Carbons? Nope. Yeah, because you see carbon doesn't have a subscript, it's just carbon. So if no subscript means 1. How many irons do we have on the right? On the right. Oh. Chicken scratch. On the right. How many irons? Forget about that crap. How many irons do we have on the right now? Carbons. Oxygens. You just told me what I need to do to calculate the number of oxygens. Yes. Left and right are balanced. Okay?
So when we're balancing, would we always tend to go to try to balance the metals first?
I usually say it doesn't matter which order you go. Make sure that oxygen and hydrogen are the last, like at the bottom of the totem pole. So you balance carbons, iron, sulfur, phosphorus, because here's the deal. If you have oxygen involved, or hydrogen involved, or water involved, there's always a space for adjustment. Okay? That makes sense? B. I'm listening.
I have a question.
Uh-huh.
It seems like there's like flexibility, so can there be more than one answer?
No.
Okay.
The reaction is always balanced the same. Always.
Okay. Two.
Should we try it? In a B, right?
I didn't look at the
Okay, no, it's fine.
Yeah, that's why these can take a while because you got to kind of plug in everything.
So here's the deal. You can solve these problems by plugging in each answer. It is pretty much a fail-proof method. As long as you calculate the number on the left, the number of atoms on the right correctly, you're fine. You can also use that method. It's not fail-proof. Well, essentially it is. It's faster if you do it right. Okay, so it's not 2. Which one is? Aubrey?
Would it be 2, 3, 3, 1?
Yes. Well, actually, don't trust me. Let's figure it out. How many aluminums are on the left? Right. On the right. Aluminums are good. How many irons are on the left? And on the right? How many oxygens are on the left? On the right? Good. This one. I'm going to give you option 2. Shall we? Question? No? So here's the deal, folks. Let's say it is a correct answer. But let's say you want to take a long route. Okay? So aluminum plus sulfuric acid gives you aluminum sulfate and hydrogen. So we're going to lay it out. The first impetus is to put aluminum, sulfur, oxygen, hydrogen. Don't. Remember, SO4 is a polyatomic anion. It behaves as a single entity. Does that make sense? This is what you should do. Aluminum, SO4. Now, if you look at the equation, all oxygens here are within SO4. You need the separate oxygen. All good? One aluminum on the left. How many sulfate anions is on the left? Just one. And how many hydrogens? On the right, how many aluminums? SO4s? Hydrogens? Okay. I do 2 aluminums, right? Good? So it's good. Then I can do sulfate. I'm going to put 3 in front of it. Everybody agrees that we have 3 sulfates on the left now. Yes, 6. What do I need to do on the right now? Everybody. Okay? Now remember, if there is no coefficient, it means 1. So, this answer. All right? We're going to do one more, I promised you. So we have magnesium chloride, okay, plus sodium phosphate. So the products of this reaction are sodium chloride plus magnesium phosphate, which is solid, it's a white precipitate. How should I build this column in the center? Should I put oxygens separately? No. So what I'm going to do, I'm going to put magnesium, sodium, chloride, and PO4. How many magnesiums are on the left? 1. Sodiums, chloride, and phosphates. Magnesium's on the right. Huh?
2.
No.
Oh.
Okay. No, that's fine. I just want to... Everybody sees that there are 3 of them? How many sodiums? On the right. And chlorides? PO4s?
I want to say 4, but
This, it's 2. So PO4 in brackets and 2 outside means that this formula unit contains 2 PO4s, 2 phosphates, for every 3 magnesiums. So we have 2 PO4 because the subscript, because of this.
okay.
Good?
So just kind of ignore the 4.
Oh, what this means, let me draw it for you. Okay? See that? We don't treat that 4 as something intrinsically meaningful. Okay? Make sense? So we have 2 PO4s. Can we do magnesium? Balance magnesium. What do we need to do?
Put a 3 in front of magnesium on the left.
Okay, it's balanced now. Can we balance sodium? Sure.
On the right.
All right, put 3. Now, the problem is that we have 3, 6, 3, 1, right? Was after the first round. And on the right, after the first round, we have, well, still 3, 3, 3, 2. I'm going to pause and ask if it makes sense for you. Just don't want it to like, oh, he writes it, therefore it is correct. Okay, so we still have the same number of phosphates on the right, still not balanced. Okay, so we go to magnesium, right? We go on sodium, but we have a problem with chloride and a phosphate. How do we balance chloride now? We have 6 on the left, we have 3 on the right. We can change this 3 to 6, right? Can we do that? We totally can. So now we have 3, 6, 6, 2. And then what? Can we balance phosphate now?
Yeah, we would have to change the left side.
Right? It's not 6 on the left, it's not 3, it's 6. So, 3 magnesiums, 6 chlorides, right? 6 sodiums, 2 phosphates. 3 magnesiums, 6 chlorides, 6 sodiums, 2 phosphates. Does that make sense? Not trying to be a jerk or anything, but in my opinion, like, you got to balance it. Like, it has to happen. Like, there is no excuse not to get it wrong, because you can count the number of atoms. If they don't match, that's not right. Try something else, okay? Okay, where are we at? Okay. We are going to take a 10-minute break, come back, and talk about the moles in chemical reactions.